section 7.2, we're going to be looking at circular functions. So circular functions are used to describe anything that's cyclic, so anything that starts to repeat itself. So some examples would include the temperature of a day. So there's often peaks and troughs there, and it goes in a bit of a wave format. You could also think about the heartbeat of a person that regularly occurs. You could also think about a piston in an engine going up and down as time goes by. All of those things that have some type of rhythm to it, we could use circular functions to describe what's going on. All right, the first part we're going to be taking a look at is a unit circle, and this is really fundamental to the entire topic. So if you can get your head around the way that the unit circle works, you'll be well equipped for the rest of the questions and ideas presented in this unit. So we've got ourselves a unit circle. Basically, it has a radius of 1 and it's centered at the origin on the Cartesian plane. Now, the unit circle can be divided into 4 quadrants. So we start in the top right-hand side. It's quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Now, as we rotate around the circle, we cover angles. So we start from this position here, which is 1, 0. If we do a quarter of a circle, that's equivalent to pi on 2, or 90 degrees. Another quarter, so halfway around, that's equivalent to pi, or 180 degrees. Another quarter, we end up with 3 pi on 2, or 270 degrees. And then finally, we finish up covering 2 pi radians, or 360 degrees. Now, if we consider some point P on the circumference of that circle, then we can have what they call a ray, which is just starting from the origin and going out to that point P. And this is often described as being the ray OP. Now, this point P can be written down as being a particular x and y value. But what you'll also see is that we can describe that point P as being cos of that angle theta, comma, sine of that angle theta. And I'll show you that in a second. So that point P can be a particular xy value, but it can also be cos of this angle theta and sine of that angle theta. And that's really important. When we're talking about the angle theta, we're talking about starting between 0 through to this 1 here and then sweeping around. So it's that angle in there. All right, I might just make this a little bit smaller, so bear with me. Okay, so I have that same diagram, but this time you can see the position 1, 0, I've got the point there. Now that's the xy. If I go straight down from that position P to where it cuts through the x-axis, I can place a C here. And so this line here could be written as CP. Now, here's my angle theta. You can also see that the ray OP, the line CP, and the line OC forms a right angle. Now, angle theta. If I go opposite over hypotenuse and take the sine of this angle, they'll be equal to one another. So sine theta equals the opposite over the hypotenuse. Now, given this is a unit circle of radius 1, it should also be clear to you that this hypotenuse in the triangle is equal to 1 as well. So sine theta equals opposite over hypotenuse. The opposite is CP. The hypotenuse is OP. Now, the hypotenuse is equal to 1, so it's CP over 1, which is just CP. So in other words, sine of this angle here is going to be equal to the distance between C and P. Now, what should also be clear to you is that the distance between C and P is just the y value, because that's where it cuts through. So there to there, where it cuts through the y-axis, is equivalent from going from C to P. So in other words, what we're seeing here is that sine of angle theta will give us the y value of the point P. And in a similar way, we can establish that cos of that angle theta is simply going to be the x part, so from here to here. And that's shown here in the same way because the hypotenuse is 1. So the whole point of that particular diagram is just to let us know that sine theta is equal to y and cos theta is equal to x. So this point P here can be described as x comma y, or it can also be described as being cos theta comma sine theta. Okay, so it's getting a bit bigger now. Moving on. Let's think about tan. If I place a tangent line at the position 1, 0, here it is. Tan of an angle theta is simply going to be equal to this point here, t, to the x-axis. So tan of that angle theta is the distance from here to there. To find that t point, all I have to do is extend the ray from O through to P until it cuts through that tangent line. That's how it's defined. So if you could imagine that now if I move this point somewhere down into the 4th quadrant, the same thing would apply. I would go from the origin out through that point P, extend, and let's say that this is where it cuts through the tangent line, then tan of that new angle will simply be equal to the distance from there to here. And that would be a negative value because it's below the x-axis. Now, depending on where you are in the unit circle, the sine of that angle, cos of that angle, and tan of that angle will either be positive or negative. I'm going to show you how we find out that we have all angles being positive in the 1st quadrant, only sine being positive in the 2nd quadrant, only tan being positive in the 3rd, and only cosine being positive in the 4th quadrant. So you do need to remember this. All schools teach crap is probably the best way of remembering it. But I'm going to show you quickly now why that's the case involving a little animation. All right, so I've got this little interactive animation of the unit circle, and I really do think it helps you understand what's going on with the unit circle, and therefore you'd be more likely to remember all those critical facts I've already explained. Look, it's not crucial that you understand what's going on here. It'll only just help you a little bit further, so don't stress too much if it's a little bit too deep for you. Okay, so as you can see, it's a unit circle, centered at the origin, the radius is 1. I've got some point P, which is this red dot here, and that point P can move around that unit circle. So we can go up to pi on 2, pi, 3 pi on 2, and then back to 2 pi. So in other words, 90 degrees, 180, 270, back to 360. I'm going to be looking at the sine function, so I'm just going to nominate the sine function. So there's a sine function. Now remember that sine of angle theta, so if I just move this across a little bit, there's angle theta here. Sine of that angle will always be the y value of that point P, and that's shown here in green. We'll go over the graphs, but the graph is shown below as well, so it does make sense of how we generate the graph, but there's that point P there. So it's the y value. Notice over here on the left-hand side, we've got the actual point. So that's that Cartesian point xy. So where I am at the moment, x is equal to 0.862 and y is equal to 0.508. The angle that we've produced is 50.5 degrees. So I'll just leave it in degrees because you're most used to that at this stage, but I can easily flick it into radians as well. But there's degrees. Okay, so there I am in the 1st quadrant. And what you can see here is that the y value is positive, so sine of 30.5 degrees will produce a positive value. And you can see there that it's that positive. All right, moving around into the 2nd quadrant. And again, you can see that the x value is negative, but the y value is positive. So sine of 121 degrees is positive. So sine of any angle in this 2nd quadrant here will be positive. Now, as we move below the x-axis, you can see that the y value is negative. So sine of any angle in the third quadrant, because I'm in the third quadrant now, will be negative. And as we continue on into the fourth quadrant, again, you can see that it will be negative again in the fourth quadrant because the y values are negative. So sine of this angle here is equal to what we have in green, the distance there, and that's negative. Okay, so I'm just going to refresh again and consider cosine now. So remember, cos is simply going to be equal to, cos of the angle will simply equal the x value of that point. So if I move to a point in that first quadrant there, cos of this angle theta will equal that blue line, which will achieve a positive x value. So first quadrant, cos is positive. Second quadrant, cos is negative. Third quadrant, cos is negative. And in the fourth quadrant, cos is positive. And you can see that shown as the x value here is positive and negative as you rotate around. All right. I'll refresh again. Let's move into that first quadrant. Okay. So let's now consider what's going on with tan. So we know where sine and cos is positive or negative, but now let's consider what tan would be. Remember, tan is defined as being the opposite over the adjacent. So in our case, it's the y value over the x value. Now the y is the sine and the x is the cos. So in this first quadrant, both sine and cos are positive. So that's positive and this is positive. So if we look at the tan opposite over the adjacent, we're going to have sine theta over cos theta, and because sine theta is positive and cos theta is positive, then tan theta is going to be positive. So what we can say there is that everything is positive in the first quadrant. So that's the A part of all schools teach crap. In the second quadrant, the only thing that's positive, because it's the S quadrant, is sine. Let's think about that. Here, that's sine theta, and that's positive. This is cos theta, and that's negative, that's the x value. Tan is opposite over adjacent, so it's positive over negative, which is negative. So both cos and tan are negative in the second quadrant. The only thing that is positive is sine. So that's why we have the S there. We move into the third quadrant, and what we can see here is that the x value is negative, and so too is the y value. So sine is negative, and cos is negative. Tan is sine over cos, so we're going to have a negative over a negative, which becomes a positive. So that means that tan theta will be positive in that third quadrant, and that's why it's a T. So in the third quadrant, the only thing that's positive is tan. We now move into the fourth quadrant. And in the fourth quadrant, it can be seen that x is positive, so that's your cos. It can be seen that y is negative, that's your sine. And of course, tan is sine over cos. So we're going to have negative over positive, which is negative, so tan is negative. So the only thing that's positive in the fourth quadrant is cosine. So all schools teach crap. And that's summarised in here. All right, so it's going to be covering some exact values. So when we're using exact values, what you're able to do is put in a certain angle for sine, cos or tan and come up with exactly what that is equal to. So that's in some kind of fractional format or involving a radical symbol. It will not just be a decimal approximate. So I'm going to explain these a couple of sets of triangles to you. And if you can get your head around this, it's going to be really valuable. And it means that you don't have to memorize a heap of standard angles and their corresponding exact values. So we're going to begin with a triangle, which is a 45 degrees, and 90 degrees. Now for this, just think about some logic here. The square root of 2 is approximately 1.41. and we've got 90 degrees there. Now 90 degrees is the largest angle inside the triangle, so opposite that will be the largest side length, so that's where the square root of 2 goes. With the two 45s, then opposite those are going to be the same side length because they're the same angle. And Pythagoras' theorem, this makes sense too. 1 squared plus 1 squared equals 2. We take the square root of that and that will give us the hypotenuse. So it should be fairly easy for you to construct this triangle. So form yourself a right angled triangle. You know it's a 45-45. The ones go there, and then we have the square root of 2. So what does this allow me to do? What is sine of 45 degrees? It's 1 over the square root of 2, exactly. What is cos of 45 degrees? It's also 1 over the square root of 2, exactly. What is tan of 45 degrees? 1 over 1, which simplifies to being 1. Let's also consider the same situation for a triangle made up of 30 degrees, 60 degrees, and 90 degrees. Just ignore this part over here. We've got 2. The square root of 3 is approximately 1.73, and there's our 1. So side lengths, approximately 1.73, 2, and 1. The largest angle is 90 degrees, so opposite that should be the largest side length. The smallest angle is 30 degrees, so opposite that should be the smallest side length. And then in the middle, we've got 60 degrees, and it should be the middle side length, which is square root of 3, which is approximately 1.73. So from this triangle, we should be able to see that sine of 30 degrees is opposite over hypotenuse, so it's exactly equal to a half. Cosine of 30 degrees is equal to the adjacent over the hypotenuse, so it's exactly equal to the square root of 3 on 2. And tan of 30 degrees is equal to the opposite over adjacent, so it's exactly equal to 1 over the square root of 3. And then, of course, I can take on the perspective of 60 degrees. Sine of 60 degrees is equal to the opposite over the hypotenuse, so it's exactly equal to the square root of 3 over 2. And cos of 60 degrees is going to equal the adjacent over the hypotenuse, so it's exactly equal to a half. And then finally, tan of 60 degrees is going to be equal to the opposite over adjacent, so it's exactly equal to the square root of 3 over 1, which simplifies to being the square root of 3. Now, of course, they're 45s and 30s and 60s. That's working with the degree format. But using these triangles, we can also work with the radian format. So 45, 45, that's equivalent to pi on 4. Think about it. If pi is 180 degrees, we have 180 divided by 4. That gives us that 45 degrees. So we know that they're the same. Here we have pi on 2, which is 90 degrees. If we look at our 60 degrees here, what's 60 degrees equal to? Pi on 3. Think about that. Pi is 180. 180 divided by 3 is 60, so that's the 60 degrees. Pi on 6 is 30 degrees. And there's our pi on 2. So we set up the same triangles, and we can do the exact values in the same way as I've just described before. So as an example, pi on 6, we know that's the same thing as 30 degrees, but what is sine of pi on 6? Opposite over hypotenuse is exactly equal to a half. What's tan of pi on 4? Opposite over adjacent, exactly 1. What's cos of pi on 3, which is the same thing as 60 degrees? Adjacent over hypotenuse, exactly a half. And that's summarised here in those yellow boxes. Now, you don't have to memorise those. Instead, what I suggest you do is get into the habit of recreating those triangles. Okay, really important. If you can recreate those triangles and put them all in the right spots, it's going to stick with you more long term, and you do a far better job of answering exact values better than trying to memorise these, because chances are that you're going to forget that. And that's what I've summarised here, just making use of, smallest side length, smallest will be opposite smallest angle, and Pythagoras theorem to construct your triangles. You can do that, you'll be in a good position. So we're going to be taking a look now at symmetry of the unit circle. And to begin with, I'm going to go back to that animation, that interactive animation. So I've begun from this position here and swept an angle of 150 degrees to get to this point here. All right, so this is my angle of 150 degrees shown there. Now what you can see here is that sine of 150 degrees will be equal to the y value of this triangle. And that y value, as can be seen on the Cartesian point, is a half. And that's 150 degrees. Now what we can do is use symmetry of the unit circle and relate this angle back to an equivalent angle in the first quadrant, back over here. So notice that that's 150 degrees, and that if I go all the way around to here, that's 180 degrees. So in this triangle, from where my cursor is to down here will be 30 degrees. So it's 150 degrees and then a further 30 degrees. So this position here can be related back to a similar position in the first quadrant. So here I am now in the first quadrant, and you can see that this is 30 degrees. Notice that the y values, that is the sine thetas, in both quadrant 2 and quadrant 1 are exactly the same. Sine of 30 degrees is equal to a half, and also sine of 150 degrees is equal to a half. So we can relate any angle in the unit circle back to an equivalent angle in the first quadrant. I'll move into the third quadrant now. This time I've got 210 degrees that I've swept through. So that's the same thing as getting to 180 and then adding another 30 degrees. So this 210 degrees I can relate back to an equivalent angle back in the first quadrant. So I can relate this back to being over here. So it relates it back to 30 degrees. But what's changed here is that now instead of having positive a half, I have negative a half. And it makes sense because the y value is negative in the third quadrant. And the same thing applies now for the fourth quadrant. So this is swept through an angle of 330 degrees. That's the same thing as starting at 360 degrees and going backwards at 30 degrees. So again, I can relate that back to the first quadrant. So if you could imagine that this point here that's in red comes up to there, basically this triangle is flipped up and the angle inside the triangle is exactly the same. So if we can relate any angle in the unit circle back to an equivalent angle in the first quadrant, we can then apply exact values to evaluate the sine, cos or tan of any angle in the unit circle. So in our case here, we can say, okay, what is sine of 330 degrees? Well, 330 degrees, the equivalent angle back in the first quadrant is 30 degrees. I can then use my triangles to evaluate that sine of 30 degrees is exactly equal to a half. And then I just need to decide whether it's a positive or negative a half. And that's based on all schools teach crap. So here in the fourth quadrant, you can see that the only thing that will be positive is cosine. So sine of 330 degrees, because 330 is in the fourth quadrant, will be a negative value. So 330 degrees is equivalent to 30 degrees in the first quadrant. So the number value that I'll generate from my triangles will be a half, but then I decide it's negative because I am in the fourth quadrant. Let's look at cosine now, and we'll rotate around the same way. So I'll just spin back to the beginning. All right, so cosine, we're talking about the x value. I might go up to here. In fact, I'll go to there. Change my mind again. We'll use 30 degrees. All right, so in the first quadrant, I've got 30 degrees. Notice that cosine is exactly square root of 3 on 2. So I can generate that from my triangles, which I explained earlier. Now, an equivalent angle in the second quadrant could be achieved by going all the way around to 180 degrees and then going back 30 degrees. In the third quadrant, I could spin all the way around, get to 180, and then add a further 30 degrees to it to get me 210 degrees. and there I'll have a negative value for cosine because x is negative. Let's just verify that. And you can see I've got that negative square root of 3 on 2. So again, what you see here is that 210 degrees, which is an angle in the third quadrant, is equivalent to 30 degrees back in the first quadrant, so that would be obtained from going from here to here. And that if you evaluate what cosine of 30 degrees is, you'll get the square root of 3 on 2. But overall, this is a negative value because all schools teach crap. Only tan is positive in that third quadrant. So when we're using symmetry, we're relating it back to an angle in the first quadrant, and we're doing it from the x-axis. So, we start from the x-axis here and we go around a further 30 degrees. But if we are in the second quadrant, we start from the x-axis and we go that way to obtain the 30 degrees. And back over here for the fourth quadrant, we start with the x-axis, go down 30 degrees. Or if we want to be in the first quadrant, we start from the x-axis, go up 30 degrees. So that's shown on my diagram here. So here we've got theta in the first quadrant, and an equivalent angle in the second quadrant is obtained by going pi minus theta. So you can see it's symmetrical. And then in the third quadrant, it'll be starting from pi and then going plus theta. In the fourth quadrant, 2 pi minus theta. So we're always going from the x-axis either that way or that way. All right, we never start from pi on 2 or 3 pi on 2. You'll notice that in my explanations, I'm purposely making use of degrees and radians because you need to know both methods. So let's look at this summary. A given angle in the first quadrant is equivalent to theta, where theta is that angle in the first quadrant, so that makes sense. The second quadrant. Any second quadrant angle can be related back to an equivalent angle theta in the first quadrant by simply going pi minus theta. Any angle that's given in the third quadrant can be related back to an equivalent angle in the first quadrant of theta by going pi plus theta. And in the fourth quadrant, we have 2 pi minus theta. And that's given there. Now what you'll see here is that after we relate it back to theta, which is the equivalent angle in the first quadrant, we then obtain, using exact values and those exact value triangles, what the number part is for our answer, and then we decide whether it's positive or negative, which is determined by which quadrant we are in. And this will make sense to us in a couple of examples. All right, so in problem 1, what we're dealing with here are working out exact values, and all of the angles have been given in degrees. So I've got my unit circle, and it's always helpful. Notice my key points, 90 degrees, 180, 270, and I've also got the Cartesian points here, so 1, 0, 90 degrees straight up will be at 0, 1, negative 1, 0, 0, negative 1, and so on. All schools teach crap. Point that begins here at 1, 0 can be rotated around. Here I've got some point given by xy, which is cos of theta, comma, sine of theta. So that's the key bits of knowledge. I've also reproduced in my notes here the two triangles involving degrees. So sine of 60 degrees. Okay, so let's look at my workings here for sine of 60. Sine of 60 degrees, so I'm going to be making use of this triangle here. There's 60 degrees. Sine is opposite over hypotenuse. So sine of 60 degrees is equal to the square root of 3 over 2, exactly. B, negative 4 times tan of 30 degrees. So for B, I've got negative 4 times tan of 30 degrees. Negative 4 times, I can find out the exact value of tan of 30 degrees. So 30 degrees, and for tan, I'm looking at opposite over adjacent, so it's 1 over the square root of 3. So it's negative 4 times 1 on the square root of 3, which is negative 4 over the square root of 3. In some cases, they like to rationalise the denominator, which just means that you want to get rid of the square root of 3 part. So I can take that answer there and multiply it by the square root of 3 over the square root of 3 to get negative 4 square root of 3 over 3. C, cos of 135 degrees. So this time I'm dealing with something that is outside the first quadrant. So 135 degrees. Let's think about that. If I start from here and rotate around 90 degrees and then keep on going, I get to 180. So obviously 135 is somewhere in between here in the second quadrant. Now remember, when I relate it back to the equivalent angle in the first quadrant, I want to go 180 minus whatever that theta is in the first quadrant. So let's make use of one of the rules here. So for C, I've established that 135 degrees is in the second quadrant. All schools teach crap, so the only thing that is positive in that second quadrant is sine, i.e. cos is negative. Cos is equal to 135 degrees. So what we can work out here is that cos of 135 degrees is the same thing as negative, because it's in the second quadrant, cos of 180 minus 135. So it's the 180 because that's going from the x-axis back here. And then I subtract from it what that particular angle is, which is that 135. So 135 degrees, which is an angle in the second quadrant, is equivalent to 45 degrees, which is an angle in the first quadrant. So if I can work out what cos of 45 degrees is using exact values from the triangles, I just need to take the negative of that. So I make use of my 45 degree triangle, take this perspective, 45 degrees. Cos of 45 is going to be the adjacent over the hypotenuse, so it's 1 over the square root of 2. Sorry for moving you across everywhere, but cos of 45 is exactly 1 over the square root of 2, and so that's negative 1 over the square root of 2. And of course I could rationalise that as well, but I'm not going to worry about rationalising the denominator, I'll just leave it like that. D. Alright, D. Let's consider D. Tan of 240 degrees. And this is probably the best way of presenting it, I think. Alright, so 240 degrees is in the third quadrant. Think about that. We start from here, 90, 180, then to 270. So 240 is clearly in that third quadrant. In fact, I can leave that just there. Alright, so tan is positive in quadrant 3. All schools teach crap. So tan is positive. The quadrant 3 angle is equal to getting to 180 and then adding that theta to it, where theta is the equivalent angle in the first quadrant, which is what we want to work out. So the quadrant 3 angle is 240, 180 plus theta, and so I work out that theta itself is 60 degrees. So the equivalent angle of starting from here, sweeping around 240, will be to have 60 degrees in the first quadrant. So that's the equivalent angle. So now I can use a bit of logic. So tan of 240 degrees will equal tan of 60 degrees, where 60 degrees is in the first quadrant. All right, and I want the positive part of that. Exact values, so I've got this position here. I want tan at 60, so tan is the opposite over the adjacent. So it's square root of 3 over 1, which simplifies being the square root of 3. So our answer for D ends up being the square root of 3. Tan of 240 degrees. 240 degrees is equivalent to 60 degrees in the first quadrant. In quadrant 3, tan is positive, so I don't need to take the negative of it, it just remains positive. I then use exact values and the exact value triangles to obtain that tan of 60 degrees is exactly the square root of 3 on 1, which is the square root of 3. Looking at E, I've got negative 30 degrees. Oh, that's a bit strange. It's not a big deal. All you do is you start from there at 0, and instead of going forwards, where you would be for positive, you go backwards. We're going back down here for 30 degrees. So obviously negative 30 degrees is going to be in that fourth quadrant. Now, if it was negative 30, I could also get there by beginning here at 0 and rotating around to 330 degrees there. So negative 30 degrees is the same thing as going forwards, positive 330 degrees. All right, so negative 30 degrees, same as starting at 360 and going backwards. so we know it's worth 330 degrees. 330 degrees is in the fourth quadrant. All schools teach crap. The only thing that's positive in that fourth quadrant is cosine, so therefore sine is negative. The quadrant 4 angle can be obtained by going 360 minus theta. The quadrant 4 angle given to us was 330 degrees, so I can relate that back to an equivalent angle in the first quadrant, and that will be 30 degrees. So here's my workings. Sine of negative 30 degrees is the same thing as taking sine of 330 degrees. And that's the same thing as having sine of 30 degrees, where 30 is in the first quadrant. We just need to take the negative of that answer, because everything in that fourth quadrant involving sine will be negative. And continue on with my workings. Sine of 30 degrees, so here's 30 degrees, is opposite over hypotenuse, so it's a half. And I want the negative of that, so it's just equal to exactly negative a half. F, I've got sine of 270 degrees. So my unit circle is up here at the top. I start from there and rotate all the way around to here, 3/4 of a circle, get to 270 degrees. You'll see that that's the same thing as being an xy position of 0, negative 1. So for 270 degrees, what I'm able to work out is that cos of 270 degrees is equal to 0, because cos is equal to x, and sine of 270 degrees is equal to negative 1, because sine is equal to the y value. So sine of 270 degrees is equal to negative 1 exactly, and that's from the unit circle. We say it's the y ordinate of the unit circle. For G, 5 cos of 45 degrees. Now this isn't too difficult at all. It doesn't even involve the unit circle. Back with our exact triangles, 45 degrees. I want the cosine of 45 degrees, so it's the adjacent over the hypotenuse, 1 over the square root of 2. So cos of 45 degrees is exactly equal to 1 over the square root of 2. And I've got a 5 lots of those, so it's 5 over the square root of 2. Here to rationalise the denominator, so I don't get a radical symbol involved at the bottom of the fraction, I just multiply by the square root of 2 over the square root of 2, which is effectively just multiplying by 1. And you'll see there that just multiplying the fractions through, we have 5 lots of square root of 2. And the square root of 2 times the square root of 2 is 2. So therefore we don't have a irrational number on the bottom. I would be accepting that answer, but sometimes in a multi-choice situation, it might present that as the correct solution. You need to understand how to obtain that answer. Okay, so looking at problem 2, and this time I'm going to be involving radians. So I've got the same setup here. Okay, so I have the same exact triangles formed, but this time the angles are given in radians. I have, starting at 0, pi on 2, pi, 3 pi on 2, the coordinates given in green. I also have all schools teach crap. And remember that any angles in the unit circle can be related back to an equivalent angle theta in the first quadrant. And these are the rules to get there. So quadrant 2 angle equals pi minus theta. Quadrant 3 angle, we start at pi and add theta. Quadrant 4 angle, we start at 2 pi and we subtract theta. So just remember that. So the first one, we want 3 lots of tan pi on 3. So here's our angle pi on 3. That's between 0 and pi on 2. Therefore, we are in quadrant 1. Now, everything is positive in quadrant 1, so tan is going to be positive in quadrant 1. Quadrant 1 angle is pi on 3. So 3 tan of pi on 3. I just need to evaluate what tan of pi on 3 is. So I go to my exact triangles, take the perspective of pi on 3. Tan is opposite over adjacent, so that ends up being just a square root of 3. So we want 3 lots of the square root of 3 on 1, and that's 3 root 3. B, 11 pi on 6. Where does that fit? 11 pi on 6. Well, that ends up being between 3 pi on 2 and 2 pi. What I think of here is just ignoring the pi part. So 3 on 2, that's 1.5. And that's 2. And now I've got 11 on 6. That's a little bit short of getting to 2. So it's just before we get to 2. Because if it was exactly 2, I could represent that as being 12 on 6. So maybe think about that with your fractional work. Anyhow, 11 pi on 6 is between 3 pi on 2 and 2 pi. And therefore, we are going to be in quadrant 4. In quadrant 4, cos is positive. Our quadrant 4 angle, making use of that rule in blue, quadrant 4 angle, is equal to 2 pi minus theta. So it's 2 pi minus theta. So it's 11 pi on 6, which is the one given to us, is equal to 2 pi minus theta. And then just translating things, so adding theta to both sides and subtracting 11 pi on 6 from both sides, I get this. I rewrite 2 pi as being 12 pi on 6. I'm still subtracting 11 pi on 6. And the result will be pi on 6. So 11 pi on 6, which is an angle in the fourth quadrant, is equivalent to having pi on 6, which is an angle in the first quadrant. So cos of 11 pi on 6 is going to be the same as taking cos of pi on 6. Remember, I don't need to take the negative of this because we are in the fourth quadrant, and in the fourth quadrant, cos is positive. Using exact values, so go back to my exact value triangles. I want cos of pi on 6, so there's pi on 6 here, and I want my adjacent over the hypotenuse, so square root of 3 on 2. And that's how we get our answer, square root of 3 on 2. Let's keep on working through this. Our next one there is tan of 2 pi on 3. So there's 2 pi on 3, that's our angle. Now think about this. If we ignore the pi parts, that's 0.5, that's 1, and this is 2/3. So we've got a half, 2/3 and 1. So we know that we have got to the right quadrant because 2/3 is greater than a half, it's less than 1. So we're dealing with quadrant 2. All schools teach crap, so the only thing that is positive in quadrant 2 is sine. So therefore tan is negative. Our quadrant 2 angle is equal to pi minus theta, where theta is that angle in the first quadrant. The quadrant 2 angle is 2 pi on 3, pi minus theta. In my next line, I add theta to both sides, and then I subtract 2 pi on 3 from both sides, and I work out that the equivalent angle in the first quadrant is pi on 3. Tan of 2 pi on 3 will be the same as taking tan of pi on 3, because that's the equivalent angle in the first quadrant, but I want the negative of that, because in that quadrant, tan is negative. Let's evaluate what tan of pi on 3 is. So again, using my exact values, take the perspective of pi on 3. Tan is opposite over adjacent. So it's a square root of 3 over 1, which simplifies to being the square root of 3. So I want the negative of the square root of 3 on 1, which is negative of square root of 3. D, sine of 4 pi on 3. So I'd start with placing down the angle that I'm dealing with, so 4 pi on 3. Now think about this again. If I ignore the pi, that's 4 on 3, which is 1.33. So that's slightly greater than 1, and it's less than 3 on 2, which is 1.5. So that kind of helps you place where you are in the unit circle. So 4 pi on 3 is going to be between pi and 3 pi on 2. So we are dealing with being in the third quadrant. All schools teach crap, so in the third quadrant only tan is positive, i.e. sine is negative. Our quadrant 3 angle, So our quadrant 3 angle is that we start with pi and then we add theta, where theta is the equivalent angle in the first quadrant. So I put my quadrant 3 angle down, so 4 pi on 3. I now take pi from both sides. And because this is expressed as being 4 pi on 3, I rewrite the pi as being 3 pi on 3. So it's 4 pi on 3, take away 3 pi on 3, and that will give me theta, where theta is that equivalent angle in the first quadrant. And now I can see that 4 pi on 3, which is an angle in the third quadrant, is the same thing as having pi on 3 in the first quadrant. So sine of 4 pi on 3 is the same as having sine of pi on 3, but I need to take the negative of that because I'm in the third quadrant where sine is negative. Using exact values, sine of pi on 3 is equal to the square root of 3 on 2, and I've got the negative of it. E, negative 6 cos of 7 pi on 6. So 7 pi on 6, so it's a little bit over 1 if you think about it that way, ignoring the pi, because basically it's simplified being 7 on 6. Pi is 1, 3 pi on 2 is 1.5, so 7 pi on 6 is going to be greater than pi but less than 3 pi on 2, therefore I'm in quadrant 3. All schools teach crap. So the only thing that's positive in quadrant 3 is is tan. Therefore, cos is going to be negative. The quadrant 3 angle is equal to pi plus theta. Of course, theta is the equivalent angle in the first quadrant. So 7 pi on 6 equals pi plus theta. I now subtract pi from both sides. And again, I want to rewrite pi so it's in fractional format that works well with my given angle. So 7 pi on 6, so I rewrite pi as being 6 pi on 6. So the equivalent angle is now pi on 6. I can see that there. Negative 6 lots of cos of 7 pi on 6 is going to be the same thing as having negative 6 lots of negative cos of pi on 6. So cos of 7 pi on 6 is the same thing as taking cos of pi on 6, but the negative of that. Using exact values, cos of pi on 6 is the same thing as the square root of 3 on 2, and I want the negative of it. So that becomes negative square root of 3 on 2, and overall I've got 6 lots of that, and because that's negative and this is negative, I end up with 6 lots of square root of 3 on 2, and then of course finally 2 goes into 6 and also into 2, and this simplifies to being 3 lots of the square root of 3. So a bit of work in that one. Look at problem 3. This again involves symmetry. Notice you're not allowed to use your CAS for it. So if sine of an unknown angle is equal to 0.34, then we need to write down the following. But what we need to do here is just assume that this theta is an angle in the first quadrant. So for A, we've got sine of pi minus theta. So what we need to do first of all is work out what quadrant we're in. Then we'll determine whether it's a positive or negative version of this 0.34. So we've got pi minus theta. This is just a little screenshot of the previous example. It shows me the unit circle, pi minus theta. That's the rule that we use to work out an angle in the second quadrant. So starting at pi and then taking theta, where theta is that equivalent angle in the first quadrant. So if we take sine of this angle theta, it equals to 0.34. Remember that sine is the y value, right? So it makes sense that it's positive 0.34. If I have the rule pi minus theta, so if I take that unknown angle away from pi, then what should I get for the sine of that? And I should get that same 0.34 because you can see using symmetry of the unit circle that it's a positive y value here and sine is the y value. But let's go through and just prove that, making use of pi minus theta. It's the only bit of information we need to realise that we use that and understand that the angle must be in the second quadrant because it's pi minus theta. So sine of pi minus theta. Pi minus theta, it's in the second quadrant. In the second quadrant, sine is positive. All schools teach crap, sine is positive. So sine of pi minus theta is the same thing as having sine of theta, which is equal to 0.34, as we said before. We've now got sine of pi plus theta. Now, if we're talking about starting at pi and adding theta to it, then we're in the third quadrant. So we're starting at pi and then adding a theta around to that. Then we're going to be in the third quadrant. All schools teach crap. So for this, you can see that sine is negative. So pi plus theta, we're in quadrant 3. In quadrant 3, sine is negative. So sine of pi plus theta is the same thing as having negative sine of theta. And from the actual question, sine of theta is 0.34, so it's negative 0.34. C, sine of 2 pi minus theta. 2 pi minus theta, there we're starting at 2 pi and going backwards by theta, so we're in the fourth quadrant. So sine of 2 pi minus theta is the same as minus sine of theta, because it's in quadrant 4, sine is negative, so it's negative 0.34. D, sine of negative theta. So negative theta is the same thing as starting at 2 pi and then going backwards by theta. And if we start at 2 pi and then go backwards by theta, then this is the rule that we'd use, 2 pi minus theta, which is the rule for the fourth quadrant. All schools teach crap. The only thing that is positive in the fourth quadrant is cos, so therefore sine is negative. So sine of negative theta is the same thing as sine of 2 pi minus theta, which is equivalent to having sine of theta but the negative of that. Sine of theta from the question is 0.34, so we get negative 0.34 here. And that's all we need to handle for those kind of questions. So it seems a little bit strange, you use positive and negative versions of 0.34, but the odd question like that does pop up. That's why we've got the problem in there. So we're now going to be taking a look at some identities, and you make use of these identities in more of the application kind of questions. They're a little bit deeper kind of questions, but they are very important. So you'll see some good examples here of it. These are our identities. And to be honest with you, the two major ones are this. Sine theta squared plus cos theta squared is equal to 1. And notice that we do write it like this. It looks like sine squared of theta and cos squared of theta, but it's actually sine of the angle, then you take that result and square it, plus cos of the angle, take the result and square it, is always going to be equal to 1. And I'll show you why in a second. In fact, I'll show you now. So looking at this particular diagram, the unit circle, I've got this position P, it's the position x comma y, which is the same thing as saying cos theta comma sine theta. So the x, remember, is cos theta, and the y is the sine theta. Pythagorean theorem, all right, we want a squared plus b squared is equal to c squared. So x squared plus y squared equals 1 squared. So cos squared plus sine squared equals 1. And that's how we come up with that identity for this. Our next major identity is that tan theta equals sine theta over cos theta. Again, I'll use this diagram. So here's theta here. Tan of theta will equal the opposite over the adjacent. Remember, y is equal to sine theta and x is equal to cos theta. So tan theta will equal sine theta over cos theta. And that's that identity. These next ones here is pi on 2 minus theta and 90 degrees minus theta. Now really this has just got to do with the fact that the sine and cosine graphs are exactly 90 degrees out of each other, or pi on 2 radians out of each other. So they're the same exact shape, except for they're a pi on 2 phased out. So, whoops, I didn't mean that. So if I just quickly flick, you can see this graph here, this is the cosine graph. And now if I flick over to sine, you'll see that it's the same shape but 90 degrees out. Alright, so here the starting point is 0, 0, and for cosine, it's 0, 1 that we start. So pretty clearly you can see that they're the same shape, except for 90 degrees out, or if you like, pi on 2 degrees out. Pi on 2 radians out, sorry. And these are the identities there. These aren't used as much. So identities 3 through to 6 aren't as common. This diagram here is not as strong as the interactive I showed you before. But let's go through and look at some application. Find all possible values of sine theta if cos theta equals 0.6. So sine theta squared plus cos theta squared equals 1. That's our first identity. We know that cos theta is equal to 0.6. So instead of putting in cos theta, I put in 0.6 and that's squared. 0.6 squared is going to be equal to 0.36. Sine theta squared is going to be the 1 minus the 0.36, and that will give me 0.64. I now need to take the square root of 0.64, and that will give me a positive version and a negative version. So sine theta could be equal to positive 0.8 or negative 0.8. So there are two solutions for sine theta that make this work. Problem 5. Given that cos of 3 pi on 8 is approximately equal to 0.3927, find what sine of pi on 8 is equal to. So we're talking about being in radians, and the key to this is to realise that cos and sine are the same graph, same function, except for they're translated by pi on 2 units. So cos theta equals sine theta of pi on 2 minus that theta that was given in the cosine. So we wanted cos of 3 pi on 8. So that's going to be the same thing as taking sine of pi on 2 minus 3 pi on 8. Pi on 2 is the same thing as 4 pi on 8. You can see that there. And so that ends up being sine of pi on 8. So what I've shown here is that sine of pi on 8 is exactly the same as taking cosine of 3 pi on 8. So our answer for sine of pi on 8 is in fact 0.3927. So to be a good set of working here, I should really write sine of pi on 8 equals, or approximately equals, 0.3927. But what I've shown here for you is that cos of 3 pi on 8 is exactly the same as sine of pi on 8. But I should go on and answer the question and say that sine of pi on 8 is approximately equal to 0.3927, because that's what I had to do. Here we have a really typical application of the first identity. So sine theta squared plus cos theta squared is equal to 1. From the question, I know that cos theta is 5 on 13. So I substitute 5 on 13 in for cos. Don't forget it's squared. So sine theta squared plus 25 on 169 equals 1. Sine theta squared will be 1 minus 25 over 169, which equals 144 over 169. To get sine theta, then it's going to be the square root of 144 over 169. And that will give us both a positive and negative version. Remember, with the square root of a fraction, it can have the square root of 144, it gives us the top, and the square root of 144 is 12, and the square root of 169, which is 13. So it's both plus or minus 12 on 13. Now, at that stage, two answers are possible. But if we go back to the original question, we know that theta, so cos of this unknown angle, is equal to 5 on 13. But we are told that theta is between 3 pi on 2 and 2 pi. That is in the fourth quadrant, sorry. So we're in the fourth quadrant here. So in the fourth quadrant, all schools teach crap. The only thing that's positive is cosine. So sine is negative. So we only accept the negative version here. So sine of theta, because we are in the fourth quadrant, is equal to negative 12 on 13. Now we make use of the second identity. The question is actually asking us to find out what tan theta is. So tan theta is equal to sine theta over cos theta. Sine theta we just worked out in this step, and that's negative 12 on 13. Cos theta was given to us in the question, and that's 5 on 13. So it's the top fraction, negative 12 on 13, multiplied by, and we flip that second fraction, 13 on 5. The 13's cancel to leave me with negative 12 on 5. And of course, 5 goes into 12 2 times with 2 remainder, so it's negative 2 and 2/5. This answer here is fine. This type of use of identities comes up quite often. You've got your first identity and second identity. You will see this less often. But this here for problem 6 is quite common. And you really need to fully understand what's happening there.